insoluble. Therefore, the basic fundamental rule to use a chromatographic system is you should be able to dissolve your sample, which is the most important thing. If I dissolve the sample, I resolve all the components. Today, the HPLC column starts, as most of you are using the HPLC columns, it starts from 10 millimeter length or smaller than that. It goes as high as 50 centimeter column or 500 millimeter column length. The diameter of the column can be as low as even 0.2 millimeter. It can go as high as 120 millimeter or beyond that. You have a host of columns over a range of products manufactured by several people throughout the world, and they call it as right from analytical column to preparatory columns. Over the last 4.5 decades, I have used the column as small as this column, as big as this column for various kind of applications. In this entire column, this is the one which provides the separation for various kind of components. Irrespective of the nature of the compound, if you have a mixture, definitely today with the technological advancement, you can have a column which will separate the mixture. Therefore, we always consider the column as the heart of a LC system. Good. Now, as you know, the column contains stationary phase and also of different nature or different kind of stationary phases which fills the column, and they are responsible for the separation of their components. The technology has grown tremendously to fill the column of different particle size. Column is an inert material. If it is not inert, it will change your compound. Therefore, the fundamental property is the column has to be inert. It should not interact with your compound nor with the mobile phase which passes through the column, which will also cause the separation, plays the role for separation. When I say column is inert, the question comes, how does it provide the separation? When I say interaction, there should not be any chemical interaction. There can be a temporary, what is called a kind of binding on the surface of the stationary phase filled in the column. Such a kind of interaction, if you understand, how does it help you to separate your constituents in an analyte, then it is possible for us to provide an excellent solution for separate all kind of components present in your sample. Further, what we should do is, today HPLC columns are available to separate everything that you want to separate. Okay. Now, further, what I should do? I should understand my sample very well. Most important thing. You should know your analyte very well. When you know your analyte very well, then you will also understand what kind of separation requirements are you looking for. Are you looking for only to separate your compound of interest? Are you looking for to separate the related substances or the impurities? Are you looking for only to isolate and extract the compound? Are you looking for quantitative analysis? What you are looking for? Define your requirements. I know what my compound is. I also know what I want. Therefore, I know how to choose my column for analysis. For that, I should understand what is a stationary phase, what kind of interaction it undergoes with respect to my compound. Once you understand the interaction, what are the various columns are available, and I know what kind of application I'm looking for, you can choose a right column for your right method of analysis you can develop, so that all the possible components can be separated. For that, what I should know? I should know what is the separation process. Many of you are already aware of this. If you look at this insert here, it is a 3-dimensional chromatogram, not a 1-dimensional chromatogram. I have a retention time in the x-axis. I have retention time in the y-axis. I have intensity in the z-axis. This is a 3-dimensional chromatogram you can map. This is the kind of technological advancement that has occurred as on today. There are 2-dimensional chromatography, you come to a 3-dimensional chromatography. But whatever the technological advance that has occurred in separation process, basically it is nothing but a triangular reaction. What do I mean by a triangular reaction? Very, very simple. I have an analyte, my compound of interest. This compound of interest, I dissolve in a solvent, in a medium, liquid medium. Mostly, I preferably use a mobile phase. Then I make that solution ready. When the solution is ready, the solution comes and interacts with the column. That's all. This now, the column is trying to preferentially retain your compound, various components. Mobile phase, depending upon the constitution of mobile phase, depending upon the flow rate of the mobile phase, it will start dislodging the molecule from the column. The moment the dislodging occurs, the analyte getting separated. So such a process is called separation process. Okay, good. For that, what I should do? I should know my sample very well. What are the things I should know about the sample? First question. Do you know the structure of your sample? And then known or unknown impurities. Known impurities because it can be part of your pharmacopoeial information, or it can be a process selected impurities. Therefore, they are known components. There can be unknown components also present, which depends upon the kind of reaction that your compound undergoes with respect to in the process or the degradation in various other aspects. Therefore, to the maximum extent possible, I should know the structure of my components that may be present. First information. Second information, probably how many number of compounds are present in a mixture? 3, 5, 10, 100, 200. For example, if it is a petroleum product, it will have more than 285 components. You have to separate all of them in a high resolution, it's a gas chromatography technique using a column length as long as 2.7 kilometers. Or now, is the sample is a readily soluble compound or it has got a matrix? Is it in the form of a tablet, solution, or it is in the form of a plant extract, or it's a plant leaf? In which form? What is the matrix behind which my compound is hiding? You have to work for that. You have to ensure that your sample is free from matrix. This is where the sample preparation plays very important role. Then I should also know, if possible, the pKa values of the sample components present. It determines what kind of mobile force I can choose. Good. Then what is the concentration? Is it I'm looking microgram level? Are you looking at the nanogram level? If it is a genotoxic impurities, am I looking at the picogram level? I should know what's the concentration range. Okay. Then above all, this is the most important parameter. You should know what kind of molecular weight of your sample, approximately at least, or the impurities that is present in your mixture. It can be, if it is below 2000, 1500, or it is 10,000, or as large as a protein, we don't know. Therefore, because depending upon the molecular weight of the compound, the column that you will be choosing will be different. Therefore, you should have molecular weight information. This is the most important parameter. I should know in which solvent system my sample is soluble. If the compound is dissolved, it can be resolved. Now, if you want to know any other data, whether there may be some new impurities, it may be present in the compound, all these informations you should pick about the sample. You should know almost lot of information. If you know about your sample very well, if you pick up all this information, just now I have listed a partial list I have made, 90% of your problem is solved. 90% solved. Very simple. Rest of things, choose a right column, choose a right mobile phase, do the separation. Now our first part is how to choose a right column. For that, I should know something about the column. Therefore, we shall discuss what are the properties of a column. We also discuss how does a separation occur. Most important information about the characteristic of a column called HETP, height equivalent theoretical plate. What is that concept? We'll explain. Understand. We'll try to understand it. If you know, we refresh ourselves. What is the role of the stationary phase? We'll try to understand that. What kind of different stationary phases are available? Now, people talk about this very quickly, quite often. Now, this is very popular nowadays for separation. I will briefly talk about core shell column also. Okay. What I will not cover in this seminar is what is called helic chromatography, chiral chromatography, and preparative liquid chromatographic system, because each itself is a separate topic and each require more than a couple of hours to talk about. Therefore, I will differ. I will not make this part of this seminar. We will talk about this maybe in the subsequent seminars. Therefore, I will not talk much because this altogether a different kind of chemistry we should talk about, because it's a very, very interesting topic, and particularly helic and chiral is one of the fantastic topic which has completely revolutionized the pharma industry, I want to say. and also food industries. Okay. Now, whenever I know my sample very well, I am going to understand what is the column I am going to choose or what are the column properties. Very good. Now, what exactly you are looking for from the analysis? You should know, you should define your requirements. You want to choose a column for what purpose? You want selectivity. You want to selectively separate some peaks? Selectivity. I want to focus only on separation, not for anything else, no quantitative analysis. At the same time, I don't want to prolong my analysis for days together. I want to make the analysis only a few seconds. Maybe I want to do a fast analysis because I want to analyze a raw material. If I want to analyze a raw material, per day I'm getting hundreds of batches. I want to say whether this batch is passing or not. Quality control work. Analysis should not take more than 10-15 minutes or 10-15 seconds. Can you complete the analysis in 1 minute or 2 minutes? You should define the analytical requirements. Then, when you are doing this, are you going to, is it that my peak should be, when the chromatogram should be, how the peak should look like? Is it an ideal chromatogram or a chromatogram acceptable by my regulatory authorities or my users? Peak shape. Most importantly, consistency, the reproducibility of the data is the analytical requirement. Then, can I use the same column again and again and again and again? Stability, very important. Then, can I use the same column for a couple of products more? Versatile. So, you have to understand what for you are doing analysis, what are your analysis requirements. Once you define, if you want to focus only on fast, what kind of column I should use? I want to look only for peak shape, what kind of column? I want to see reproducibility and fast analysis, which I can compromise, which I cannot compromise. I am looking for everything? One single column will do for this purpose? You have to define. So analysis requirements plays a very important role. I know what kind of sample it is. I know what kind of column I am going to choose, so I am going to understand the theory. I also know what kind of what is my requirement for analysis is. Once you define all these parameters, life becomes simple. How to get an ideal chromatogram. It's an ideal chromatogram. Why I call it as an ideal chromatogram? I have drawn a vertical line here in this chromatogram. I have seen, when I drawn a vertical line here, you can see very clearly, I have a base. This is the retention time. This is direct response. If you look at this peak very clearly, you draw a line. You do this on a piece of paper. Then what you do is, exactly at the center line, what you do is, you just fold your paper. When you do the folding, the peak just come on the left-hand side upslope, and the peak has gone down. This is called a down slope. Both will superimpose upon each other. When they superimpose upon each other, it will appear as if it is a single peak, which means when from the center of the apex of this peak, at each portion, you can very clearly see that the peak is each upslope as well as the downslope are equally spaced. Whether it is at the 70% of the peak, or at the 50% of the peak, or at 10% of the peak, at each portion of the chromatogram, the peak is just can be folded and juxtaposed. Both slope value are identical. This is an ideal chromatogram. It's an ideal chromatogram. Okay. Now, how best you can get this ideal chromatogram? That's what you should do. You have to choose color. It is very difficult to get. Can I get this? It's very difficult. But can I come very close to this? The answer is yes. How close I can come to this? For that, the column you should know very well. If you look at this peak shape, which I was talking about, you have to correlate this peak shape with, first of all, column parameters. If you recall our last webinar, I introduced two terms there, what is called capacity factor and selectivity factor alpha. The capacity factor and selectivity factor both are related to the flow of the solvent when it passes through a column. When the mobile phase enters into the column along with your sample, the sample comes in contact with the stationary phase. We call it as the sample will come in the form of a band. We call it as a zone. The rate at which the sample is coming in contact with the stationary phase depends upon the flow rate of your mobile phase. Therefore, I call that as a linear flow velocity of the mobile phase. Then, when the mobile phase, which carries your sample, comes in contact with the mobile phase, stationary phase, then your sample is distributed between the part of the sample is distributed between the mobile phase and the stationary phase. Volume of stationary phase, volume of the mobile phase. This is a distribution function. Now, when it is being distributed, this distribution factor can be called as capacity factor. The velocity with which the solvent flows depending upon the length of the column and the retention time to which the compound is retained. If I am able to correlate the volume of the stationary phase, the volume of the stationary phase, volume of the mobile phase, and the capacity factor, this is the equation where I can tell how fast the sample can migrate to the stationary phase. This is called capacity factor. Okay, good. Now, this capacity factor, I can correlate to the retention time of your compound as K prime is equal to retention time of your one compound analyte minus initial injection time divided by time at which it comes in contact with your stationary phase. Now, if I have got two components, the two components, one component is B, A, another component is B, then I introduce a term called all selectivity factor alpha, where alpha is equal to retention time of component B divided by retention time of component A. Of course, the starting time you have to subtract. The retention time of the selectivity factor and capacity factor can be related to the actual physical happening inside the column. Okay. Now, how do I understand that my column is able to provide a preferential migration of the components present, for example, component A present in the mixture to the surface of the stationary phase? How does it does one? This is where the concept of theoretical plate has been introduced. It is called height equivalent theoretical plate. What does it mean? Very, very simple. Theoretical plate is very, very simple. How do you say that's very simple? You take very hexane, take toluene. You know toluene boiling point is high. Hexane boiling point is less. Toluene is 110 degrees roughly. Toluene is around 60, 40 to 50 degree boiling point. It evaporates also very high. Now, you take this mixture in a flask, apply a small amount of heat. Now, what happens? Because the boiling point is low, your hexane will come first. If you keep the boiling point, the temperature constant, at that temperature, all the hexane will come out. It means I have distilled hexane from toluene. It means one distillation cut, one temperature at which the entire volume of the hexane has been taken away from toluene. Such one distillation cut is called one theoretical plate. The HPLC column is nothing but it has got several distillation cuts. It can be 10,000 distillation cuts and they are called as theoretical plate. How do you define that? Imagine this is the length of the column. I have got n such a distillation cuts. Therefore, 1, 2, 3, 4, 5, I. Therefore, so many I can equally divide the column depending upon its ability, and I have divided n segments. It is called plates. And this is the length of the column n. So one height equivalent is nothing but h is equal to L by n. Height equivalent theoretical plate. That's all. Now, how many, what is the concentration sample present? It is very simple. If you see the concentration nth plate, I can calculate through this mathematical interaction relationship. And such a distribution is called Poisson distribution. It depends upon how much is the total volume of the mobile phase passed through the first segment. And also the initial concentration. From that, what we'll understand? I will understand that the concentration distribution I can correlate to the standard deviation. This is called the basic theory of, or a plate theory of column. That's all. Very, very simple. Now, this plate theory is an ideal theory. It has got some limitations because I have assumed here when the mobile phase is passing through the column, at every segment is equilibrium, constant. The equilibrium also very rapid. This assumption I have made. When I made this assumption, then what happens? It passes through the column, and that is not an ideal case. Therefore, people have modified the theory and introduced a theory called Van Dimter equation, which is called H is equal to A plus B by U plus C into U. U is the velocity of the linear velocity of the mobile phase. Note, it's a very, very simple equation. What are these three? These three A, B, C are characteristics of a chromatographic system. It actually gives you the real information, what is happening inside the column. The column is packed by particles of 5 micron to 10 microns. I do not go into the details of column packing. This is a huge topic. When the columns is packed by particles then there's a small, because the packing density will change depending upon the size, the length, and inside the surface of the column. Now, therefore, in the packed column, when your sample passes through, solution passes through, what will happen is it can follow different path. The first different path is defined by the first constant called A. Second one, when it passes through, if the gap is very small, due to the interaction that is occurs between the molecules, between the surface of the stationary phase as well as your sample, there's a diffusion factor is involved. It is nothing but the concentration gradient. Molecules move from high to lower concentration spontaneously. That's a second parameter. The third one, we call it as how effectively you transfer entire sample from the mobile phase to the column, or from the column preferentially back to the mobile phase. Mass transfer. Different molecules enter and leave the stationary phase at different times. This is why all the three parameters are related, and related to height equivalent theoretical plate. H is equal to A plus B by U plus Cu. This is a graph depending upon the linear velocity, how each constant behaves. B by U reaches at lower value, it increases, the velocity increases. It is a straight line here. Here it is a parallel. A is almost constant because there is no variables involved here. Now, therefore, the plate theory assumes the equilibrium is rapid. The rate theory gives a true equilibrium information to us. Now, in this, what happens? Now, this picture will tell you very clearly what exactly happening. This is the particles. You can see here, stationary phase. Mobile phase entering. Some mobile phase passes through here. Some mobile phase passes through here. There's this is an analyte. Now, between the stationary phase and the compound and the analyte, an interaction can occur, and the unequal pathways. The second thing is, I have an analyte here. This is my mobile phase. This is my stationary phase. This is a concentration profile. How much my analyte is released from the mobile phase preferentially to move here, which is very important. You should know about that. So depending upon that, the forward-backward diffusion will occur. This is called molecular diffusion. The third one is mass transfer. At the end of when my stationary phase releases from the mixture, the preferentially analyte 1 or analyte 2 or analyte 3, how much it goes back into the mobile phase from the stationary phase. C term. This is how it is being picturized. Now, if you look at this more detail, the different pathways called eddy diffusion. It is also called as here, the path is very tortuous path from the particle, and it moves in the form of a parabolic motion. When it moves in the form of parabolic motion, the nature can be such that the path can be totally be different. Because the path is different, it causes a little bit of band broadening. Now you understand what is exactly happening inside the column. One of your job is the band broadening should be small, as sharp as to get the ideal situation. Okay, remember this. 2, molecular diffusion. It is a longitudinal or a molecular diffusion sample components due to concentration gradient inside the column. It is not necessary. For example, molecular A, analyte A, entire analyte will not be simultaneously transferred to the mobile phase. It can be a small change in the concentration gradient. it causes a small spread in the peak. Therefore, you get a profile of a band, you don't get a sharp peak. It contributes. And that is why it depends upon the mobile phase velocity. There's a diffusion coefficient. It plays an important role. Fantastic. 3, mass transfer. What do you mean mass transfer? It depends upon how your mobile phase is able to dislodge your analyte from the stationary phase, partition coefficient. It also depends to what extent your sample, the components in the sample is able to get solubilized in the liquid phase, relative solubility. It also depends to what extent it has got an ability to get absorbed to the surface of the solid phase. Not only that, both are entire process depends upon temperature. That's why column temperature plays a very important role in the entire analysis. Therefore, it is not only recognize the diffusion longitudinally, but also axially. When you do all these things, there's a continuous transfer of sample, both from the leading and trailing edge zone. Therefore, if you look at the peak broadening line, this is the ideal peak, what you are seeing here. This is the actual peak. The stationary, this is a stationary phase, and this is what exactly happening in the mobile phase. There's a small time lag between the equilibrium distribution of the molecules. This is what exactly happening inside the column. If that is the case, how I should talk about? I should talk about the column resolution. This is where the alpha comes into the picture, and which also directly proportional to the square root of the number of theoretical plates and square root of the length of the column. And it can be given by this equation, 2 into TRB minus TRA divided by width of the peak. This is an ideal situation which most of you are familiar with. The resolution is 1.5, which that is what FDA insists. Your separation is excellent. Good. I know a little bit what are the properties which plays the role in column separation. I know the theory. I know what is theoretical plate. Good. Now, how to choose the column? I will start. I will not talk much because most of us, in many of the applications, we use reverse Swiss column. What is a reverse Swiss column? Very simple. In a normal column, the silica is non-polar. You use a polar solvent. Change the polarity of the solvent. Higher the polarity, better the retentivity. Therefore, you do separation. You just reverse this. Make your solvent polar and your column non-polar. The moment I make my non-polar, it means nothing but C18 or octa dicyclane. This is a typical non-polar column that you are having. So liquid chromatography, right? The interaction will be hydrophobic compounds. The compound does not directly dissolve in water. So compound will dissolve, but it will not hit the surface. Depending upon the hydrophobic nature of the compound, you can provide the separation. Now, in the case of a non-polar, if the column which you are using is a phenyl-based column, the mechanism hydrophobic interaction, we call it as pi-pi interactions. When we call it as a pi-pi interaction, it is nothing but a dispersion force that is present in the bonded phase. What does it do? You can see here, I use a aromatic compound here along with this functional group, which causes a phenyl column. It can be used both as a reverse as well as a normal phase to some extent. This is a sino-propyl column, which we call it as intermediate polarity, where retention is a mixed mechanism of hydrophobic, dipole-dipole interaction, or pi-pi interaction. What are these? We will see very quickly now. Now, before that, the particle size plays a very important role. How to choose a particle? It depends upon the dimension, length of the column, internal diameter of the column, and also the particle shape, the irregular or spherical shape, and also the average particle diameter varying from 3 to 20 micrometer. Then surface area also plays important role, because entire physical absorption process is totally surface chemistry. Okay, now how to choose the particle characteristics? Very quickly, if you look at this picture, this is a bonded type. It's a monomeric column. I can have a silica here where I can attach all the silica with the C18, everything is attached here. In a monomeric steric protected column, there is isobutyl column. It is nothing but more than one functional group of attached. Similarly, in the case of a polymeric column, if you use a horizontal polymerization, I can say that each silica is linked through an oxygen here. This is a polymeric. The horizontal polymeric basal column plays a very important role to reduce the tailing of the peaks. Therefore, bonded, even it's a polymer in the monomeric type, it's a single point attachment of a bonded phase molecule. In the case of a polymeric column, it's a multi-point attachment of bonded phase. This is a typical particle size that you talk about. This is a pore. There are two things. The typical pore silica particles are the most common that is used for the greater column capacity and availability for a wider options. The particle size varies from 1.5 to 5 micron range. This is the typical solid core, and this is a pore shell that you are talking about, and this is where the diffusion or the perfusion of the particle occurs. If you can look at this picture, and also before I talk about this pore size, one more parameter I have to talk about is called end capping. Capping of exposed also the short hydrocarbon chains after primary bonded group. What do I mean by end cap? At the stationary phase, you attach a TMS molecule. When you attach a TMS, what happens? It minimizes solenoid interaction and protects the silica support from dissolution when you use the mobile phase. Therefore, end capping columns are useful when you work at a higher pH. Now, this is a end capping, a typical end capping I can say, where I have attached a TMS group along with the silica column to protect the column. Similarly, if you look at this graph, I can see this spherical particle size. This is a irregular particle size. Therefore, spherical particle offers lower back pressure. When I offer a lower back pressure, I can use the long, so the column lifetime becomes much longer, which is very, very important, so that I can use for, when you want to talk about the reproducibility of the analysis, I can use the same column for a longer duration. And another parameter is what is called the part, depending upon the particle size, lower the particle size, better is the back pressure may be high, but the resolving ability is much, much better. I can, if I use a 3 micron, I can separate maybe 10 peaks. If I use a 10 micron, I may be separating only 3 or 4 components. I will show an example for that. Okay, when it comes to surface area, it's very, very important, because surface area plays an important role in order to make the resolution much better, because depending upon the larger the surface area, retentivity of an analyte, and the surface becomes much better. Therefore, effectively, the separation between the two components is much better. I can have my resolving power more than 1.5. depending upon the components. So lower surface area very quickly, especially important for in gradient analysis when we do. Pore size, larger pore allows larger solute molecules. Therefore, whenever we work with the molecular weight of the compound less than 2000, we choose pore size less than 150 Armstrong units. When the molecular weight is greater than 2000, choose the column with the pore size 300 Armstrong units. This is where the pore size plays a very important role. That is why when I define about your compound, look what is the molecular weight range that you should look for. Because if I know I am working less than 2000 or I am working more than 2000, if I know that information, I can choose a column of right pore size to make my separation successful. That is why this parameter is very, very important for us. Now, the monomeric binding offers increased mass transfer with the higher column efficiency. Whereas in the case of a polymeric column, the bonding offers increased column stability, particularly when highly aqueous mobile phases are used. Polymeric bonding also enables column to accept higher sample loading. If the impurity is less than 0.1% or its chromophore is not the same as that of an API, I want to inject more amount of sample whether impurity is present or not. Polymeric bonding phase columns are very effective for us. Therefore, bonding type plays an important role for us. Then comes carbon loading. Higher the carbon loading generally offers greater resolution on longer run times. So lower carbon loading shortens the runtime. Therefore, the carbon loading also plays an important role in the bonding phase. Then apart from column loading, I should look for column selectivity. When look for column selectivity, it depends upon the composition of the stationary phase as well as molecular structure of the solute. And if it's a hydrophobic interaction we are talking about, or are you talking about what is called steric, that also depends upon the steric interaction that you are talking about. Depending upon the nature, you have to choose the column accordingly. Now, there are 8 kind of interactions that occurs when you want to select a column depending for your separation of the compounds A and B. And what kind of interaction compound A is going with respect to the stationary phase, whether it is a hydrophobic interaction or it is nothing but a steric interaction or hydrogen bonding or anything else. Now, if you go beyond this, you can see here the hydrogen bonding coupled with acidic or basic group, you can see the kind of binding it has. If it is a basic binding, it is an NH group or a cation exchange. If it is a dipole-dipole interaction, it is nothing but a cyanide column. I have got dipole here, positive negative charges, positive and negative charges present. Now, if it is a pi-pi interaction between an aromatic solute and either a phenyl ethyl group, the column will be totally different. It can be both can be a pi-pi interaction. This is also a pi-pi interaction or a combination of several interactions is possible. Now, this is what is called, if the compound is a metal complex, then any chelating solution you have to use. You have to look for that. These are the various kind of interactions that a column can have with respect to choosing a right column stationary phase. You have to know the interaction very well correctly. Now, when you talk about the shape selectivity, now the most important thing is when you talk about I have to say polymeric column. When this is a typical separation, it's a mixture of 13 polycyclic aromatic hydrocarbons. I could able to separate in 30 minutes 13 columns. If you use the monomeric column, you can see how poor the peaks are separated. All these peaks are completely merged. Therefore, now when you do this, how often I can use, how I can measure the column efficiency. The column efficiency can be measured by the theoretical plate. That is height equivalent to theoretical plate, H is equal to L by N. Column efficiency as a function of particle size and type, where H should be, N should be very large, thereby H becomes very small. Lower the value of H with the larger velocity, you can see 2.7 micrometer superficial porous particle gives a better result compared to all other particles. Therefore, this is a cross section of a halo particle of 9 nanometer per electron micrograph. You can see here is a typical separation where we are able to separate more than 9 peaks in just in 0.7 minutes, around 40 seconds. Not more than that, because we used a column with a 2.7 micron particle size of C18. Now, what kind of the purity of the silica also plays a very important role. It depends if the surface of the is contaminated by metals, then the purity affects the acidity of the silica. Because it affects the acidity of the peak, it leads into tailing and poor recovery of the sample. Therefore, when they make a column, the purity of the silica support is extremely important for us. When it comes to the core shell columns, this is a typical core shell, the schematic diagram of core shell and silica particle. I will show a better picture for you. And in this core shell column, I will skip this slides and I can show you how does, you can see here A value, B value and C value in entire this core shell columns. In all these parameters, if you look at the very carefully how the sample is distributed. If you can look at this graph, this is a core shell column. Actually, this length is only 1.6 micrometer in inner shell, where a sample is trying to interact. But effectively, this diameter outer portion is around 2.6 micrometer. Therefore, totally the particle size for a diffusion purpose comes out to be around 2 micron. You can see very clearly. Therefore, my mass transfer becomes much better in this case. Okay. Now, if that is the case, then I can tell you core shell, when you see, I can show you a core shell column with the Van de Graaff parameter. I can see very clearly for a particle, if you look at the total HTP is almost parallel from 6 to for longer velocity. Thereby, my efficiency of separation, fast analysis, and also resolution, all the parameters can be done very well, because the transparticle mass transfer is excellent. Diffusion is also very good. Longitudinal is also possible. Therefore, effectively, the H value is equal to so low. You can see here, a 1.8 micron particle gives you peak more than 2 minutes, whereas a 2.6 micron column gives in less than 1.5 minutes. This is a typical analysis I have shown you. I have taken from literature. Therefore, to quickly summarize, I have given a small glimpse of the concept of theoretical plate. I have introduced some of the characteristics and parameters of the column. I have shown you different columns and a little bit of chemistry behind it. How a 2.6 micron particle size core shell column is able to provide the much better, faster separation with the better peak shape, very close to the theoretical peak that I have shown initially, I am able to achieve. Therefore, I am ready to choose and use column to successfully separate all my analyze. Thank you all for your attention.
Oh, thank you so much, Dr. Venkat. Column is such a critical component of any HPLC analysis. So thank you so much for covering all the parameters to consider before selecting the column. So since column itself is such a huge topic, so we shall be covering the remaining part in our next webinar. So there are a lot of questions by our viewers. So I'll just read out a few questions so that you'll be able to answer them.
Sure.
Yeah. So we have one question from Mr. Mahadev Bera. So can I separate cyclohexane, dicarboxylic acid, terephthalic acid, 4-carboxy benzaldehyde, benzoic acid, and toluic acid in single injection?
You will be able to separate in a single injection when you have got carboxylic acid and aldehydes with you by using gradient elution.
So the next question.
Gradient elution has to be, because the gradient condition should be chosen such that you start with the non-polar solvents initially and then end with a polar solvent.
Yeah. So another question from same Mahadev Bera is, my main product is TPA, and it's around 99.96% terephthalic acid, and the impurities present in the product is cyclohexane dicarboxylic acid, which is around 0.001% to 0.005%, acid 4-carboxyl benzaldehyde, which is around 0.0001% to 0.0025%, and benzoic acid and toluic acid. So he wants to, I think it is a continuation of the same question from the question one.
So this is where you have to check with the quality specification of the product. He is already having the purity of the compound 99.96. If you add all the impurities, it comes 0.04%. Unless there is a specific impurity for which the concentration should be this much low. That's what the specification says. He has to look for not the UV detector, should look for a mass spectrometer detector to look at the specific impurities. Otherwise, it depends upon his quality control specification sheet.
So next question is from Mr. Malleshwara Rao. So I was developing a method for AKBA acetyl ketobenzaldehyde acid, but the retention time keeps changing every day. I tried everything, no problem with the system, column, sample, or mobile files. I tried running another analyte. The retention time varies less than 0.02 to 0.05 minutes.
Because I don't know what kind of mobile phase he's using. He'll be using a buffer mobile phase where the pH of the solution should be adjusted, should be kept below the pK value of the product.
Thank you. So another question from Mr. Mangeshwar. So which column should we use for the analysis of oil compounds?
Fatty acid columns.
Oil compounds. I think there's not much specific about the compounds that you wanted to do. It's just mentioned analysis of oil compounds.
If it is a castor oil, for example, oil compounds, we use what is called FFAP column. It is called free fatty acid columns, FFAP column. So normally we do not by HPLC, but we do by gas chromatography, high temperature gas chromatography.
So there's another question from Kabita Sharma. Does the ideal chromatogram of nucleic acids at psychological pH of the cell still remains the same even after DNA or RNA gets denatured due to changing pH in the HPLC columns?
No, it will change. It will change because the pH plays very important role in HPLC analysis.
So another question from Pooja, sir, how the molecular weight affects the column?
Yeah, it's a very good question. If the mass transfer between the stationary phase and mobile phase depends upon two parameters. One is the solubility, next is the molecular weight.
So another question from Mr. Akshay. So the RT is more than 10 minutes, then it is 10% plus or minus limit. If the limit itself is 1 minute, so I'm not sure what the question is. What is the 1 minute plus limit if it is there?
Can you read the question once again?
1 minute plus minus limit is the limit available. If RT is more than 10 minutes, then if it is 10% plus minus limit. So,
no, normally the retention time limit 10% is too high. We don't, the retention time cannot change more than 0.5, 0.6%. If it changes retention time more than that, more than 0.5%, if it is say 10 minutes, 10 minutes can become only maximum 10.05 or 0.8. It cannot become 11 minutes. If such a thing happens, it means he has to look into the mobile phase conditions.
So there's another question from Pranali. What solvents are appropriate for LCMS?
Volatile solvents, mostly we go for a formic acid, acetic acid, or buffer. We use with ammonium formate, 0.1%, 0.2% ammonium formate buffer, or 0.1, 0.5 formic acid, along with acetonitrile or methanol.
So there's another query from Mr. Govinda. So is there any chance of solvent recovery after the whole process of HPLC?
No, not recommended, because it will always get contaminated. You don't use the solvent for anything else once the HPLC analysis is done, because it is exposed to the compound. Number two, it also undergoes what is called microbial contamination.
Another question from Pooja again. So what is the best regeneration method for C18 columns in stationary phase?
There is a procedure, there is a 10-step procedure is available in a troubleshooting given. Probably in one of our coming seminars, we will be giving a separate talk on troubleshooting HPLC and MS. At that point in time, probably we will cover this topic. Okay. We have a series of, one is called C18 column the regeneration, C8 columns regeneration, ammonia column, NH column, how to regenerate it, CN column, how to regenerate. This is separate procedures are there. We will share with the audience at that point in time. Probably you have to wait some after 3 or 4 web seminars.
Okay. So there's another query from Mr. Muthu Kumaraswamy. So my compound is in basic nature, amine as a functional group. So which column is used for related substance analysis?
We have to use the end capping higher pH withstanding columns, where the pH will go as high as 13.0. So such a column has to be used for this purpose.
So another question again from Pooja. So how do we prevent the unequal pathway in column before analysis?
We normally use spherical polymer based columns. Spherical particle polymer based columns, where the particle size should be around 3 to 5 microns.
So another query from Mr. Balaji K.S. The range of theoretical plates for a 5 micron pore size column
is if the column is 25 centimeter length of the column, it should be around 15,000.
So another question from Mr. Rahul Patil. So how much sample can I inject on my LC to avoid band broadening?
Normally, you should not inject more than 5 to 8 microgram per ml. per ml. Because when you make a solution, we normally use a 5 to 10 micrograms of sample, not more than that, by weight.
So there's a query from Mr. Tirumala. Please tell us the good column caring procedure. Probably he wants to know what are the procedures that has to take for good column care.
What is the question?
What are the procedures to follow to have a good column care?
Yeah, we will be giving a talk on troubleshooting, there we will do we will cover a particular portion called column care. In that we will incorporate all the details. It will happen maybe after 3 or 4 seminars.
Okay.
In that we will cover that one.
Mr. Prabhakar Pandit says, can I analyze simultaneously the sugars and organic acids with single column undetector?
No, it's not possible because the sugar needs a refractive index column detector, whereas the carboxylic acid we use a UV column because detector requirement is different. Therefore, it is very difficult to use the same system for the purpose.
So, a question from Mr. Rahul Patil. Any specifications to column length and injection volume? Or is there any correlation between column length and injection volume?
Yes, there's a very big correlation. The column length is small. The column loading, if you begin automatically, quantity of stationery is available becomes very small. Therefore, the column loading has to be controlled depending upon the column length. Normally, if it's a 25 centimeter column, we can inject as high as even 20 microgram. If the column length is only say 50 millimeter, 55 centimeter, it is 50 millimeter, we use only not more than 2 to 3 micrograms.
So there's another query from Mr. Sudhir Shinde. Sir, we have a product paracetamol 325 mg and tramadol 37.5 mg effervescent tablet. Since our formulation is water soluble and we are facing related substances as per USP, column is phenyl. When we analyze conventional tablet with some method, conventional tablets are not showing any single peak other than paracetamol and tramadol, but what our effervescent tablet shows how to resolve.
He has to use change the detector. He has to use either a light scattering detector along with UV, or that's the best way of doing that, so that we can see the impurities. Light scattering detector is a universal detector, better than RI detector.
Mr. Balbin is again, I think, how to handle for the long life of each column, which we are going to cover in the next chapter.
The ideal situation is use one column for one product.
So another question from Professor Ananta. So what to do when the column starts bleeding?
When the column starts bleeding, it means there is a leak at the inlet port of the thing, and that the inlet port, there is a filter, that filter needs replacement.
So what is the shelf life of a column? This is a query from Mr. Muthu Ramaling.
You can spoil a column by 1 injection, or you can use a column even for 1000 injections. If you take care of your column, normally a column will last around 500 to 600 injections.
So another question from Mr. Rohit D'Souza. What is the equivalent column I can use instead of Porter's Cortex T3 3 mm 100 mm into 2.7 micrometer?
No, I don't have that catalog. You have to look in a catalog.
Okay, so probably we'll answer this query. We'll take your query and then we'll answer it separately.
Yes.
So for the separation of phenols, which column should be used? This is a query for separation of phenols. So which column is suggested? This is a query from Mr. Khaja Moinuddin.
You can use a normal C18 column. You can use.
Okay.
C18 column, or you can use. I don't know in the phenyl what are the other functional groups are present. C18 column should do the job. That should be a problem.
So another query from Ms. Pooja. So how to reduce the peak tailing and fronting?
One of the ways by reduce, first is controlling the sample loading, number one. Number two, you have to choose the mobile phase such that it is correlated with the pK value of your sample. Then you can control both.
So then another query from Kabita Sharma. Does the polarity of the mobile phase affect the chirality and twist of nucleic acids when separated via HPLC MS? Will this LU give the accurate mass to charge ratio in MALDI-TOF analysis?
In the case of a chiral column, the polarity of the mobile phase plays very important role, very important role. Because that is why I kept talk on chiral columns separately, because there exists every possibility. Sometimes the mobile phase after even 10 injections spoil the chiral column. The resolution you lose. Therefore, you have to be very careful in choosing the mobile phase for the chiral column as per the manufacturer's advice. You cannot do any kind of, you cannot use the mobile phase as you like. You cannot do that.
Another query from Sushma Chandar. Please suggest a column for separating catecholamines.
C18 will do normal. Catecholamine is very simple. C18 column, 20% carbon loading.
So another question from Mr. Muthu Ramalingam. So can we wash the column reversely?
Not advisable, not advisable. Because in the column inlet, there is a frit is there, which prevents deposition of the particles, what is called some of the metallic contaminants to go inside the column, which will be soft. If you reverse and use it, you will contaminate the column. Never try that one.
So there's another query from Mr. Nishant Ahar is again asking how to regenerate the column. Probably we are going to cover that in the next webinar.
Yes.
So coming down, sometimes my compounds RT is shifting small amount when increasing the concentration. Is it due to the column or any other issue?
Pardon?
Sometimes my compound RT is shifting in small amounts. So when increasing the concentration. So when it increases the concentration, there is a shift in the RT. So is it due to the column or any other issue? This is a question from Tirumalai.
No, which call, the question is not clear, because unless we know the details of the columns they are using, it's very difficult to answer this question.
Okay, we can take that question separately. What is the limit of resolution in related substance?
Normally, we keep a resolution should be 1.5. Even it is 1.2, it is acceptable, depending upon the, if it is above 1%, should be 1.5. If it is below 1%, 1.2 resolution is okay.
Okay. Yeah, I mean, the questions are pouring again. We should adjust pH of mobile phase as to keep our compound fully unionized or fully ionized.
Which one?
I'm not sure. This is a question from Mr. Prashant. Ms. Pinko, should we adjust the pH of mobile phase as to keep our compounds fully unionized or fully ionized?
It depends upon the separation that you are looking for. What kind of separation you're looking for? Because this question is a little bit abstract to answer fully. I can have one last question now.
Yes, sir. So you have a query, or I'll just read out. There's a lot of questions actually.
Now, probably what I request the audience, when they ask the questions, many of the questions are, the details are not there with respect to specific analysis. Therefore, what we request the audience is, since we give the topic, probably they have to make the questions more specific so that we can give better answer to them. So some of the answers, it's very, very general, is very sketchy.
I understand. Yeah. So what we request everyone is probably you can all be more specific so that it'll be easy for Dr. Venkat Manohar to answer your queries. In fact, what has happened is many of them are actually continuing the questions in the subsequent question. This thing. So we are not able to correlate because there are a lot of questions. We have got more than 50 questions to answer. So if we can be more specific in the first instance, it would be fine. So I think we have almost answered all the queries as of now. Only one last question, since you said there's one query from Mr. Srirangam Jagdish. What kind of columns can I use in petroleum separation? So this will be our last query.
Petroleum separations, we normally use same C18 column only, but the mobile faces will be totally different. Very careful about the mobile face.
So what we'll do is like, in case if you have any more queries, we request you to like send out your queries to my email ID, which I'll be sharing in the chat box. So you may write to info@spincotech.com, and we will take your queries and then we'll ensure the doctor answers all your queries. So please write out to info@spincotech.com. And regarding the there was a lot of requests for the presentation and this thing. So we'll discuss with doctor and we'll see if it is possible to share the presentation. And of course, at the end of this webinar, you'll all be receiving a survey. Please, we request all of you to answer, fill up the survey. So it will be useful for us to make it more interesting and more useful for you. With this, we thank you all for joining this webinar, and we'll be continuing the second series of the webinar, which is the HELIC product, HELIC compounds, and then the preparative columns, and these things will be covered in our next webinar. Thank you all for joining. So have a nice weekend. Thank you, Dr. Venkat.
Thank you.
So we'll be closing this call now.